So this section is on light. We already talked about waves and sound. So this one is particular for light waves. Because light waves, there's a lot of similarities to sound waves, but there's a lot of differences. Because of, well, really just the energies involved. So let's talk about this. So, here are what you're supposed to get out of today. Number one, you're going to prove that light can be represented as a wave. Prove that light's quantized, and you can list in the correct order all the different types of electromagnetic waves. It's kind of a misnomer because it's really just the one type, just electromagnetic waves. But we have them broken up into a list, that way we can talk more specifically about different pieces of it. So, this first light kind of talks about the speed of light. We already talked about the speed of sound, it's about 760 miles per hour. We had a whole lab on measuring it. It's significantly different to have a lab measuring the speed of light. And the reason for that is because, well, for most of the time, scientists thought that the speed of light was infinite, or it was just too fast to be measured. Galileo was the first to hypothesize that it does have an actual speed, it's finite, but it was too fast for him to measure with his experiments. It wasn't until 1926 that American physicist Albert Michelson was actually able to recreate one of Galileo's experiments, and with more advanced equipment, he was able to measure the speed of light. So he measured that value there. Today we tend to just round it to 3 times 10 to the 8 meters per second, or 186,000 miles per hour. To put this in perspective, if you were traveling at the speed of sound, it would take you a couple of hours to get from here to New York City. If you're traveling at the speed of light, it would take less than a second to get from here to New York City. Like, it is not just a little bit faster, it is tremendously faster. Matter of fact, if you're traveling at the speed of light, you could go around the entire Earth over 7 times in 1 second. It is that fast. So, it's no surprise I had some trouble measuring it. And so here at the bottom we see V equals F lambda, which is our wave equation. But sometimes you might see it written as C equals F lambda, because C stands for the constant speed of light, which is, for our purposes, we just round to 3 times 10 to the 8. On the next couple of slides, we have a lot of definitions. So these are, I think, pretty straightforward. They're relatively important definitions, because I will use the words. But we have luminous versus illuminated. A luminous body emits light waves, so things like sun, candle, they make their own light. Okay, if you stick the sun in a closet, it will still have a lot of light because it makes its own light. But an illuminated body just reflects light waves. So like a moon, mirror, your desk, if you stick those things in a closet, well, it's not going to make any light, and so it'll be dark in the closet. So if I stick you in a closet, can you see anything? No. So you're more of an illuminated body. But it should be noted that these terms will be different depending on which part of the spectrum you're talking about. So in general, if we don't specify, well, we're talking about radio waves or whatever, then we're talking about visible light that you can see with your eyes. Okay? So here, luminous bodies make light that you can see with your eyes, and illuminated bodies don't make light that you can see with your eyes. Make sense? All right. So there's these 3 categories of matter that doesn't make its own light. Okay, so if it makes its own light, doesn't really apply here. But transparent materials allow light to pass through, and it permits objects to be clearly seen. So, like a window is transparent. Translucent materials allow light to pass through, and all light passes through, but it diffuses it, so you can't really see what's on the other side. So it gives you an example there, but another example is just the lights in this room. Like if you look at the lights, it might appear that the lights in this room is just like one single bulb. It's not. It's actually a row of LEDs. then last but not least, there's opaque, which means you cannot see through it. Okay? So black and white. So those are pretty standard things, and again, some of these things you hopefully have heard of before, like probably you've heard of transparent. You may or may not have heard of translucent or opaque, and so, you know, you should write down the words. Definitely you should write them down if you don't know them. But, you know, write down what you need to. So do y'all have any questions so far? So it's just a bunch of definitions. When it comes to light, essentially light has two different theories about it. One theory says light is a particle, the other one says light is a wave. And so for a long time there was arguments back and forth about which one was correct. Like for instance, Newton supported the light as a particle standpoint because, for instance, you can see the light coming through that little window there. It comes straight through. There's no funny business. You don't see any diffraction. You don't see any other things occurring there. So, you know, it's like, okay, we'll go straight through, so it must be a particle, like a ball. But then there's other people, mentioned Huygens, who thought that light was a wave, because under certain circumstances, you can get the light to spread out. For instance, when light passes through a prism, it spreads out. And the reason why it spreads out is because the different colors of light have different wavelengths. And so, to understand this, they're all traveling at the same speed, okay? But when you go from one medium to another, like say air to glass, they change speed. So when they change speed, if it's coming at an angle, it will result in them turning. So think about it like this: if you imagine like a very large red vehicle, so think of like a big red Mack truck. Okay. So think of like a big red Mack truck. So that's a big, long vehicle. But then think on the other end of the spectrum, of the violet end, think of a violet smart car, a very small thing. They can both drive down the highway at the same speed. And let's not even think of the speed of light. Just think of like 60 miles per hour. Can both of those vehicles drive down the highway at 60? Yeah. And if they're both going the same speed, they'll stay right next to each other. Let's talk about the front bumpers. Like they'll be right next to each other the whole way. But then let's say, okay, now we tell them both to turn 90 degrees right now. Well, they can both turn 90 degrees, but they're going to have to slow down to do that. Does that make sense? Which one's going to be able to slow down quicker? The big 18-wheel red truck or the small purple smart car? The smart car. And so as a result, the shorter wavelengths turn more than the longer wavelengths because they're bigger. So bigger wavelengths are more difficult to turn. Now they're both traveling the same speed. And I think that visual helps a little bit, and that's the thing that makes it look like a wave, because waves have different frequencies and they bend or refract, and whenever light passes through a prism, it comes out in different colors. And it always goes from red to blue in that order, because red has the longest wavelengths and your blues have the shortest wavelengths, and everything else in between just falls out in between. And so we have these two theories. And so some people are like, well, it's one or it's the other, and they argue for years about this. But in truth, you can kind of think of it acting as both. Really, what light is it's a wave that comes in patterns, which we'll talk about here in a second. Basically, the definitive thing that killed the hope of possibility of light being a particle was the double slit experiment. And so the thing that I did for y'all with the water waves, that you saw like water waves come in, it hit two splits, it diffracted from each slit, which, if you throw a ball through a hole, it goes through one hole or the other. But waves will go through both holes at the same time, and then they'll diffract, and then they'll interfere with each other, and they'll create an interference pattern after that. So in this case, if you put like a wall here, it'll create a interference pattern on the wall. So that's what kind of killed it ever being really thought of as a particle again, but it's not quite a wave. And there's a couple of videos there I encourage you all to watch. So, this slide talks about the photoelectric effect. And the photoelectric effect is important for several reasons. The main one is, essentially, we have this effect. And what the photoelectric effect is that if you shine a light on a piece of metal or something, it's possible for the light to make electrons come off of that piece of metal. That's what you're seeing in the picture, like light coming in, electrons being ejected. What does this mean? Well, we can do this experiment, all the time. But the reason why this has to do with particle wave duality is the fact that, like, okay, at this point we had accepted that light was a wave, it diffracts and interferes, which ball can't do. But what's very interesting is that if you shine a light on a piece of metal, let's say it injects some electrons, okay, you measure that as a current. Well, if it's just a wave, if I just make the light brighter, I should get more electrons. That's not what happens. Making the light brighter doesn't give you any more electrons than if it's, pretty dim. If you want more electrons, it turns out you need the right frequency of light, not brighter lights, which is interesting. And so that was actually explained by Einstein in 1905, and he talked about that the reason why this happens is because these waves come in packets, which he called quanta, what we call photons. And these packets, you can kind of treat them, some people, that's why they say wave-particle duality, but it's really just a wave that comes in a indivisible chunk. Like, you can't make it any smaller than this. And that's what the word quanta means, is that when you cut something up, you get to a point where you can't cut it up anymore. And whatever that lowest amount that you can cut it down to, whether it be energy or mass or whatever, we call those chunks quanta, because they're quantized. And any one of these individual things we call a quantum. And so that's what Einstein called it. He said that they come in little quanta, little packets. We don't call them quanta anymore, we call them photons. But I want you guys to understand that the whole term quantum mechanics is talking about mechanics, which you guys already learned last semester. But it's talking about the fact that when you cut things up, they can only go down to a very certain size. And that's what quantum mechanics is. It's talking about what happens on that size level. It's mechanics, but they can only be done in so small of a packet, right? You can't cut it up anymore. So for instance, we used to think protons, you couldn't cut them up. Turns out you can. But we haven't found a way to cut up electrons. So maybe electrons are a fundamental quanta for matter. Like photons are a fundamental quantum of light. So I wanted to kind of explain that because that's one of the things that the photoelectric effect showed, is that it was the frequency, not the intensity. And what's really interesting is that it's a particular frequency for a particular material. If you shine a light, let's say violet light or purple light as shown here, let's say it injects 12 electrons per second, okay? But then you make the light brighter, more intense, it won't give you any more electrons. But then if you change the frequency, maybe you go over to like green, and you get, say, instead of 12, maybe you get 16 electrons per second. Oh, okay, now I get more. So then you think, okay, well, violet's on this end, so if I keep going this way, maybe I'll get more. But then after you pass green, you go to like yellow and then red you only get like 8 electrons per second. And so it's not just any particular frequency. It's not simply these have more energy than these. It's because the material that's holding the electrons needs a certain amount of energy, kinetic energy, for these electrons to start roaming free. And the frequency of the light shows you how much energy it has. And so higher frequencies have higher energy, lower frequencies have lower energy. And one of the results of these things called quanta is that when these energy packets come in, the electron will either absorb it or it won't. And it will absorb it under certain circumstances, if the energy is a certain amount, certain quanta. If it's not the right amount, it will not absorb it. So that is one of the biggest things about the photoelectric effect, is that it proved that light comes in these little packets, these little photons. Okay, so what does that have to do with your light? You don't care. But aside from that, we use the photoelectric effect for many things in your daily life, like solar panels, garage doors, or TV remotes. Like, these are things that we use the photoelectric effect for. I'll give you a good example of the photoelectric effect. You ever play Garage Door Olympics? You know what I'm talking about? Where you're in the garage, and the garage door is open, and you got to get outside, but you got to close the garage first. So you got to push the button. But you got to get to the end before the door closes. But what else? Yeah, you got to jump over the sensor that's not there. And when you learned about that, you were probably pretty young. And so it looks real funny if you don't know that sensor's there, because you got to go in the door and over the one. Okay. So I want to talk about that sensor. That little sensor there, what it is it uses infrared light, and we'll talk about infrared here in a minute. But it uses a beam of light that you guys can't see, but just think of it just like a little laser pointer. And on one side of the garage, it just shines that light to the other side. So one side is literally just like, think of it like a laser pointer. On the other side, it's the receiver. The receiver is where the photoelectric effect is occurring, because that wave will come in of a certain frequency, and it will cause a certain number of electrons to be ejected. And then we will take those electrons and we'll run them through a circuit, and they'll get put back, so everything's neutral overall. But the current flows through the circuit, and your little circuit will look at it and go, okay, if this much current is flowing, then the beam is connected. If that much current doesn't flow, then that's what causes your garage door to stop in reverse direction. And so that's easily done by a broken beam, right? If you break the beam, you're not going to have as much energy, so therefore not as much electrons get ejected, so therefore not enough current. But what's very interesting is that it can also happen the other direction. Like if you just take a flashlight and shine it on the sensor, it'll cause probably more current to flow, and that will also trip it, and it won't close. I only know that because growing up, during certain times of the day, if you went to close my garage door, because of where the sun was in the sky, it would shine down on the sensor, and it wouldn't let the garage door close. I only figured that out by default because we couldn't get the garage door to close. And so what we found out is that I just happened to be standing in the right spot where my shadow was cast on the sensor, and the garage door was fine. And so it was funny because once, like, we didn't know photoelectric effect or any of this, but we just knew that if the shadow covered it, we were fine. And so I just remember, like, our solution was, like, whenever the garage door wouldn't close, my mom was like, get out of the car. Like, go over there, like, stand. In retrospect, it would have been a lot easier just to, like, tape an index card to it. But I wasn't a very smart kid. All right. But the photoelectric effect is just something that happens. And again, it happens for a particular frequency, right? Not necessarily how bright or dim it is. It's all about that frequency, which is why, like, your TV remote can work. You push different buttons, it sends out slightly different waves, infrared waves typically. But they'll be different for each button. And so each different frequency will cause a different current to flow in your sensor, and then different things will happen with different currents. So hopefully that makes some sense, but it's a pretty important thing. Okay, let's talk about this wave. We talk about light is a wave, and it's a three-dimensional wave, and it's weird to visualize. Like, this is how it's typically visualized here, is that we would say it's traveling down the x-axis, and it's oscillating back and forth in both the electric plane and a magnetic plane. And those two planes are always 90 degrees from each other, and 90 degrees from the direction of travel. I think this visualization is neat, but it doesn't really make any sense. So if you think about like a radio antenna. So the way a radio tower works for like your car radio is these towers get a lot of energy and they run electrons up and down. So let's just imagine one electron. If you imagine one electron going up to the top of the tower and coming back down. Okay. That's what the thing does. But what happens is if you imagine all of space as being filled with this medium, it doesn't exist, but we're pretending like if this is like the ocean, right? And you take, instead of electrons, just take like a big like bowling ball and just like throw it down to the ocean. It's going to make this wave. It travels out in all directions. Does that make sense? That's essentially what's happening with the electron. When you move the electron up, it'll make like a crest that travels out in all directions, move it down and make a trough that travels out in all directions. But in the end, like I said, it's coming off in little packets, these little photons. So they're quantized, but they're still spreading out in all directions. And it's produced by an accelerating charged particles, not simply particles moving. They have to be speeding up or slowing down. And the greater they speed up or slow down, the more waves come off. So they're very interesting to think about. This is the electromagnetic spectrum from beginning to end. There really is no beginning or end. But we focus on the middle because that's where we can see. So if I start over here, we have gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and radio waves. So on this end with radio, we have long wavelengths, and they have lower frequencies, so they have lower energy. Okay. Now remember, wavelength and frequency are inverse. So as I move this way to the other side, down here by gamma rays have a higher frequency. They're increasing in frequency, but it's making the wavelengths shorter. But because they're more frequent, they have more energy. So things on the gamma ray end of the spectrum tend to be kind of dangerous, and things on the radio end tend to be kind of benign. So there's a chart over there behind my desk on the wall. That black chart is all about the electromagnetic spectrum. And it has a lot of detail, like an insane amount. It will show you different frequencies. It will show you different wavelengths. It will show you what frequency GPS is. It will show you what frequency channel 11 is. Because they have to be, because here's the thing, this is a big, long spectrum, but each frequency is a particular spot on the spectrum. Like when you listen to the radio station, like 106.1, that is a particular frequency on the spectrum. And when somebody's using it, nobody else can use that frequency. Like how many 106.1 radio stations do we have here in the Metroplex? Just the one. Because you only get one for each frequency. So like if there's a TV station on a particular channel, there's only one on that channel, at that frequency. Because as big as the spectrum is, it has a limit to it, right? And what's really interesting is some of you have probably been on road trips where you have to like, listen to the radio, and when you go from like say here to Waco, the radio stations change. Because they're not changing so much because they have to, but what we've done in this country is we've said that each particular frequency belongs to a radio station. But here's the thing. We're here in Dallas. Do we pick up radio stations from New York City? No. So we can give them both the same frequency, but then we also have to designate how far they're allowed to operate. Because there will be a point at which the radio station's waves can overlap. And whichever one you hear is essentially which one's stronger at that point. And so we say that we have like our DFW stations, and they are designated to operate in the DFW area. And that is a certain geographical thing that the FCC regulates. And here's the thing. Who said 106.1 got to broadcast at that frequency? Well, technically, in this country, it's actually us. People. Fun fact about radio stations and TV stations is that they're using these airwaves. And we, as a group of people, have allowed the FCC to regulate it. And the FCC gets to hand out certificates of who gets to broadcast at which frequency and whatever. But did you know that whenever a radio station or TV station, like it happens, I mean, it's different, it kind of depends on their contract. But like at the end of their contract, like I said, it's a 10-year contract with the government. At the end of that 10-year contract, on the radio station, they will broadcast a message, at various times throughout the day, and they'll say, hey, our licensing agreement is coming up. If you have any complaints, please send them to this location. And what will happen is the government body, the FCC, will look at the complaints if people have them and see if it's justified or not. And if a radio station has too many complaints, the FCC will pull their license and they will no longer be a station. So yes, these stations you're on AM, that's going to be in kilohertz, right? The way that the carrier wave works is it is the frequency that you tune your radio station to. The modulator is going to be the song or whatever that you're actually listening to. And so it comes at this frequency, you tune your radio to that frequency, it receives the wave, and then your radio will decode, take the carrier wave out of it, and then just play you the moderator. And so an amplitude modulation looks like this. Can you see how this is getting bigger and smaller with the modulator wave? And so you can see the carrier wave, like it's the same frequency as it was, but it just gets bigger and smaller. Frequency modulation actually changes how often the wave comes in. And that's why when you have FM stations, have you ever noticed that like you can do like 106.1, but there's no 106.2 or 106.3? Because they have to allow overlap because they're changing the frequency. And 106.1 doesn't just operate at that frequency, it goes up and down because it's the frequency modulated station. So frequency modulation sounds better because there's more waves per second, because it operates in a million hertz range. So it sounds a lot better than AM, because AM sounds a little static a lot of times because it's just not as frequent, because you can lose parts of the signal. With FM, there's just so much signal, you can lose parts of it, and it doesn't really matter. But AM has a really unique property because it's amplitude modulation. More power gets you a lot more distance. And as a result, there was a radio station that operated in the 1950s up until like 1964, 1968 or something. It was actually based out of Tijuana, Mexico, which is important because they didn't have the FCC in Tijuana, because it's a different country. And as a result, they built a radio station, and it had the call sign XREF, and it was known as pirate radio, because, as I mentioned before, there's radio stations in like Dallas, and there's radio stations in Waco. Which one do you think makes more money, a radio station in Dallas or a radio station in Waco? Dallas. As a result, if the radio stations had no regulation, and they wanted to, if the radio stations in Dallas simply just turned up their power, they would blot out the radio stations in Waco, and you wouldn't be able to hear any of those local radio stations. But that's against FCC regulations. But if you build a radio station, say, a different country, it would be subject to their laws, America's laws. So when they built XREF in Mexico, it was an AM station, and they just cranked up the power. And I'm talking about a lot of power. It said that on a cold, clear night where the air was pretty still, this radio station could be heard as far away as London. That's a third of the Earth's surface. It was also said that if you lived in Tijuana, Mexico, your plates would pick up the radio station, because there's so much dang power. So like if you had like a plate like sitting on the wall, it would start vibrating, just really to start making the music or whatever they were playing on station. Eventually, the American companies got the Mexican government to shut down that one. That was the most famous one, but more of them popped up over time. But the thing is they were just so powerful that anything on that frequency in America, it would just blot them out. And it didn't matter. Because in this country, we had regulations to keep, that from happening. Radar waves are just another type of radio wave where the, like I said, it's a very low frequency, very large waves. And here this talks about the Doppler effect and stuff. We already talked about that. I'm not going to spend too much time on that. Do y'all have any questions here? Okay, so then let's go up to microwaves. Microwaves are a bit shorter. So to put this in perspective, radio waves are very large. Like they could be the size of the Earth or bigger. We stopped having what we call radio waves about 1 meter. So like this is like the smallest radio wave you can get. After that, they become microwaves. Most microwaves are about the size of a football, maybe a little bit smaller, maybe a little bit bigger. But if you ever microwave something in your microwave, those tend to be about 2 inches, the size of those microwaves. And they can set up a standing wave inside of your microwave. And the standing wave is what causes your food to have hot and cold spots. Like hot spot would be an antinode, cold spot would be a node. What's interesting is most people think that, this turning of the plate here will evenly cook your food. It will help. It's much better than the food staying stationary, but it will not get rid of these nodes and antinodes. They're just going to be there. And so the best thing you can do to evenly cook your food is literally just give it some time. Like put it on for 30 seconds and then let it sit. And put it on for 30 seconds and then let it sit. Because the areas that are getting hot need time for the heat to distribute to the rest of the food through the process we know as conduction. I really think microwaves are funny, but they get a bad rap because people use them very weirdly. Like if you think about how you cook things on the stove or in the oven, if you apply those same techniques to the microwave, your food would be fine. But most people don't. Most people take all this time to like cook something on the stove, or you cook macaroni and cheese on the stove, like stir it and put it in the water and blah, blah, blah. People just slap stuff in the microwave and they put it on for 30 seconds and they're like, why didn't it work? I'm like, do you just crank your oven up to 500 degrees, throw something in there and just be like, okay, in 2 minutes, that'll be fine. That's not how cooking works, but for some reason you throw it in the microwave and you just expect everything to be perfect. There are actual recipes and things that you're supposed to do in the microwave, but most people just ignore those and put it on for a minute and hope for the best. Which honestly, it comes out pretty good considering you're not really doing anything like that. So, anyways, microwaves. Infrared is the next part of the spectrum. So again, a little bit shorter. This is a little bit harder to visualize how short these waves are. But they're higher frequency. And I mentioned earlier that you guys do not make visible light waves. But it turns out anything that is, well, greater than 0 Kelvin will put out electromagnetic radiation because of the heat coming off of it. Now, if you make your own heat, or if it's just hot because it's next to something hot, it will put off this electromagnetic radiation. And the size of that electromagnetic radiation, well, depends on its temperature. For most objects, humans in particular, because of our body temperature, the waves that we put off are, well, in the infrared part of the spectrum, the far infrared part of the spectrum. And so if you have like an infrared camera, you can see that. Another type of infrared camera is like your security cameras. They put out infrared waves that are near the visible part of the spectrum. And that's how those cameras work at night. So they don't necessarily need a big spotlight, but they throw out infrared waves so that you guys can see it. And so I have a camera right here that sees things in infrared. So I'm going to pass it around and look. And it looks, all these pictures. Now, in the end, does it have to have like this particular coloring to it? No. It doesn't have to have this particular coloring to it. That's just whatever it's like. Because here's the deal. Can you see an infrared? No. And so the camera's just making up some colors and slapping them on there. But, like I said, it'll work. And, here this is showing you like his hands through a plastic bag. And the whole deal is like, this is opaque to visible light, but it's not opaque to infrared light. All right, so I'll let y'all pass that around. Now we get to the visible light part of the spectrum. We like to think of it kind of in the middle. Maybe it is, maybe it isn't. But it's hard to say what's in the middle when we haven't found the evidence. So visible light is from about 400 to 700 nanometers. So to put a nanometer into perspective, if you had a meter stick, can you imagine a meter stick with all the little millimeter marks? So if you took a millimeter, like one of those tiny little marks, and you divide it into 1,000 marks, to a millimeter of a millimeter, and you cut that in half, that would be the wavelength of green light, 500 nanometers. That's really small. Okay? And here are the wavelengths. So, red is this, violet is that, and so on and so forth. So the colors always come out red, orange, yellow, green, blue, violet. That is it. Now, if you're looking at the spectrum, you might look at that and go, okay, I agree with red, but what's wrong with violet? There's a bunch of black, but I mean, does that look like violet to you? Not really. And the problem is that these definitions actually come to us from Isaac Newton. And we, as a culture, have actually changed the definition definition of violet. Nowadays, we associate violet with what color? Purple. But back in the day, violet wasn't a purplish color, it was a dark blue. And I can easily prove that because you guys know the first part of the poem, that roses are red and violets are blue. I think it's really weird that we call violets purple, even though the poem's like, roses are red, violets are blue. And nobody has a problem with roses are red. They're like, yeah, roses are red. Why do we say violets aren't blue? This is a stupid thing. No. Violet used to mean blue, like dark blue. That's what the poem's talking about, is that that's what violet makes violet's violet. It's just a dark blue. Anyway. My point being is, violet used to be dark blue. Now we say it's purple. But according to 400-year-old definition, violet is that color. So each of these colors has a wavelength, and so if you can find the wavelength of the light, then we can say, oh, it is this color. Now we might be a little bit more specific. We might say, oh, this really bright green here. We're not just going to call it green. We're going to call it chartreuse or whatever. And that's fine. But the whole deal is that we have a very specific frequency for each color. Everybody okay with that? And they always come out in this order in passing through a spectrum because of the different wavelengths. Then we get into more light we cannot see. So we come to ultraviolet. Ultraviolet, X-rays and gamma rays, most of that stuff is blocked by our atmosphere. And actually most microwaves are blocked by our atmosphere too. But infrared and some radio waves get through. Most of the ultraviolet gets blocked. What's interesting is most of you guys have heard of like UVA and UVB. And what that refers to is actually two windows in our atmosphere that allow these different frequencies in. Like UVA is a particular set of frequencies, kind of like green light or whatever. And UVB is a different set of frequencies. And so both of these can get through our atmosphere. UVB is closer to violet, so it can penetrate through the atmosphere into our skin. And so you notice it says like skin surface, so think of that like a dead layer of skin on top, but the epidermis is right underneath that. That's how far UVB penetrates, and then UVA goes a little bit further down into the dermis layer. But what's interesting here is it also shows like UVC. Now UVC should be blocked by our ozone. It usually is, except for the fact that we've damaged our ozone and we have some holes. And so sometimes the UVC gets through as well. And UVC is an even higher frequency, or sorry, it's a lower frequency, so it really shouldn't get through, but sometimes it does, because we have broken our planet. Now what happens is when these rays come in, they have so much energy that they can cause skin to burn, because it's too much energy. So the short-term damage is that it does sunburn, okay? So it says here that the high energy light penetrates about 4 cell layers into your body. Your skin is generally like 7 layers, so it doesn't go past your skin, UV doesn't. But when it gets in there, it can damage, it can cause sunburn, because it just literally burns it up, like, putting fried chicken in the microwave for too long, it just burns it up. But longer term, what can happen is that these UV rays can come out and they can damage the cells, and the cells are repairing themselves, they can repair themselves incorrectly. And that's what causes like cataracts, wrinkles, skin cancer, stuff like that. Because it's just your skin being damaged. Here, we're talking about X-rays. X-rays penetrate even further than ultraviolet. They pretty much just go through your whole body, but they tend to bounce off of really dense things like bones. And so X-rays can be useful for taking a picture of like the inside of you. But just like ultraviolet is dangerous, X-rays are more dangerous. But we don't tend to encounter those out in the wild because our atmosphere blocks all X-rays and gamma rays pretty much. So that's good. But just like UV can damage your cells and cause, like, say, skin cancer, X-rays can do the same thing. But generally, X-rays are an acceptable risk because just like when you go outside, do you just get cancer? No. But if you stand out there long enough, yeah, you're going to have, the odds of you getting skin cancer from the sun will increase, okay? possible that it could damage you and, and cause you to have cancer, but the odds are very low. Not as low as UV, but very low. And the thing is do you just normally get exposed to X-rays? No. So there's almost, I'm not going to say there's no risk, but it's a very, very low risk of anything happening with X-rays. Now you might say, okay, but why should we even do this? When there is a risk of cancer, and there is. It's not zero. Okay, it's low, but it's not zero. So why do this? Well, the whole deal is well, why do people take X-rays? Most of y'all have had X-rays, right? Why do you have an X-ray? Yeah, exactly. They can see inside you without cutting you open, because yeah, you may or may not get cancer, and there's pretty low odds that you get cancer, but if they cut you open, that is a very serious thing. And there's a lot of bad things that can happen when they cut you open. And in general, they don't want to cut you open unless they really, really have to. Okay? So X-rays are a real good way of looking inside without actually going inside. And so generally the risk is very acceptable for X-rays because it's like, yeah, you could develop cancer, but it's like, well, why don't we just look inside and make sure things are okay as opposed to just cutting you open and being like, oh, we didn't need to come in here at all. Because surgery is always a big deal, I don't care how minor it is. And then last but not least on the electromagnetic spectrum is gamma rays. Gamma rays are actually named, they were actually originally called gamma radiation because they were discovered by a scientist by the name of Marie Curie. And Marie Curie, I'm not going to spend too much time on her, but she is pretty remarkable, I guess was. First of all, you guys should know that she is only one of 5 women ever to have won a Nobel Prize. I think she was the first. But beyond that, she is only one of 4 people that have more than 1 Nobel Prize. And she is the only one who has more than 1 Nobel Prize in different disciplines. She has one for physics and chemistry. Everybody else who has 2 all got them in like the same thing. They've got 2 physics points or whatever. So hers is pretty unique, that she's the only person to have 2 Nobel Prizes in different disciplines. So that's pretty intense. And I'm not going to get too much into her research today. It's more for our next unit. But when she was doing her research, she saw these particles coming off of the stuff she was researching, and she named them alpha, beta, gamma, which sounds all fancy or whatever, but literally she didn't know what they were, which is why she called them that. She literally just called them ABC. Because for those of you who don't know, if you're talking about the Greek alphabet, it goes ABG. It goes in the first 3 letters of the Greek alphabet. So she didn't know what it was, so she just called it Mystery A, Mystery B, and alpha, beta, gamma. Now it turns out alpha particles are actually just helium nucleuses. So once we figured out what a helium nucleus was, which was after she did this, we went, oh, that's the same thing as this. Okay, cool. So sometimes we call them alpha particles, sometimes we just call them helium nucleus, because that's what they are. Beta is just an electron. Again, she didn't know that at the time. But what's interesting is that gamma is not a particle. It is a gamma ray. It is a wave of electromagnetic radiation, and she was the first one to discover it. Which is why we still call it gamma, because we don't have any other name for it. Like we had electrons, and then we just realized, oh, this beta stuff you're talking about, that's an electron. Like, okay, cool. Gamma, we didn't know what that was. It's just a very high energy wave. And like X-rays can go through most of your body, not bone. Gamma rays will go right through you. You need something like 6 inches of lead or like a foot of water to stop gamma rays. They're pretty good about going just through stuff because they're so dang small. But the problem is they're so small, but they have a lot of energy. So if they happen to hit something when they go through you, they probably won't stop, and they'll probably just tear through whatever they go through, which is why they tend to damage cells. Here, when we talk about light, these 2 definitions aren't particularly useful for us, but they're going to be useful in your life. Because if you go buy a light bulb from the store, you have luminous flux and illuminance. And what this means is luminous flux is literally how much light is coming off of this light bulb. Okay? And so if you have 2 light bulbs and you're considering using them for the same situation, it'll tell you how much luminous flux measured in lumens. Usually I won't say luminous flux, it'll say 450 lumens. That's literally the rate at which light is emitted from the bulb. Okay? But there's another thing to consider, and it's called illuminance. Illuminance is the light falling over a particular area. And that makes a little bit more sense if you think about it just like a flashlight. If you take a flashlight and I hold it up right here against the wall, it'll make a very small circle, right? But that circle will be pretty bright. Are you okay with that? But as I move the flashlight back away from the wall, that circle will do what? Gets bigger. But here's the deal. The amount of light coming off that bulb doesn't change whether it's a big thing or small thing. So this thing gets bigger, but it also gets what? Dimmer. And that's what illuminance is. It's like, okay, well, if this thing was 6 feet away, how much light is falling on this area? And so it's an interesting thing because if you were to do, say, let's say you owned a home and you were doing some construction. Let's say you had lights that were just this high up here. And you're like, okay, I want to put a vaulted ceiling in here. So I'm going to tear out the ceiling and I'm going to make one of those big ceilings go up another like 5, 10 feet. Well, if you just simply move those lights up, they're not going to be bright enough. Even though you did nothing to the lights, but because you moved them further away, it's going to seem dimmer down here. So you're also going to have to upgrade the light bulbs that you put up there because they're going to have to put up more light because now they're going to be covering a larger area. That makes sense? And so, like, these are things that I'm not going to like quiz you on these things too much, but I want you guys to understand that these are things that you will have to deal with in your labs, right? Like, eventually one day you're going to have to buy a light bulb. Which light bulb? Kind of depends on what you want. But there is such a thing as too much light, I will tell you that much. And so we say that the light from the source spreads out in all directions. And we say this is due to what we call the inverse square law. Because if you take this flashlight example I had, let's say it starts a meter away. Well, if you double the distance, you make it 2 meters away, it doesn't cover twice the area. It covers 4 times the area. And so the light ends up being 4 times weaker if you simply double the distance, which is something like I was mentioning about the illuminance that, if you simply go from like say 8 feet to 16 feet, you don't need bulbs that are twice as bright. You need bulbs that are 4 times as bright to get the same light down on the floor. Does that make sense? So, not that y'all plan on doing a whole lot of that, but it's just something to think about that, like, you don't really think, you go, oh, it's twice as far, okay, I could get a light bulb twice as bright. No, no. You need a significant increase in your power from those things. Here, this talks a little bit about shadows. I'm not going to get into too much detail. We've kind of talked about shadows before, but it's caused by diffraction. And so diffraction is where the light or the wave bends around the barrier. So here it gives us the example of like the Earth being the barrier. So light's coming from the sun. And so some of it will diffract around the edges. And so you get 2 regions of shadow, the umbra and the penumbra. The umbra is the part that is completely dark. Like no light from the sun gets into the umbra. Okay? And for the Earth, the umbra goes off many hundreds of thousands of miles in space. And it's possible for the moon to pass through the umbra and be covered by the Earth's shadow. Now the penumbra is significantly larger than that, but it's a partial shadow. And so that just means it's a little bit dimmer because like here, essentially if you're looking at, let's say, like the bottom area here, the light from the sun, from like this side of the sun is being blocked by the Earth. But the light from below the sun down here is still lighting up that area, which is why it's kind of a partial shadow. It's a little bit darker, but it's not like the umbra. Umbra should be completely pitch black. Now, if you're talking about like a total lunar eclipse where the moon goes into the Earth's shadow, at first it really looks like, oh, that thing is going to get into the Earth's shadow and be completely blocked out. But typically, once it gets in there, it looks very red. And the reason why it looks very red is because red is a very long wavelength, and when it goes through our atmosphere, it is the last color of light to be absorbed. And so when light passes through our atmosphere, the red doesn't necessarily get absorbed, and some of it can make it all the way around to the other side of the Earth and come out, and it will light up the moon as a deep red color. There you go. Lunar eclipses are actually pretty common. They could almost happen once a month, but because the moon's orbit is slightly inclined to the Earth's shadow, it doesn't happen every month. But yeah, about once a year, you should get a nice lunar eclipse, just because of geometry and everything. It doesn't necessarily happen every year. Sometimes you get 0, sometimes you get 2 or 3. Just, depending on how things line up. This will be our last slide for today, and this is on polarization. And so when we talk about light polarization, this is because light is a transverse wave. And so if you think about like a rope, like let's say I had a fence, like picket fence, and I run a rope through it. If I shake the rope up and down, the waves will go through the fence, okay? But if I shake the rope side to side, the waves will not. They'll be blocked by pickets. And that's what polarization is that something like the sun gives off waves in all directions. It doesn't care. But you can have something like a picket fence, like literally we can make polarized sunglasses that have these little pickets built into them. And they'll essentially block half the light that's not going in the right direction. But that's not really the point. I mean, really, if you wanted less light, you would get, tinted glasses, like sunglasses. Now, your sunglasses can be both polarized and tinted to dramatically reduce how much light comes in. But sometimes, like the light will hit a surface and become polarized as it reflects off of that surface. So, for instance, when light hits something like a flat puddle of water, you get this big glare coming off of it, but what you may not realize is that glare is polarized. And if you wear like polarized sunglasses that can cut the glare in a particular direction, you'll get kind of what we see down here in this picture. That we have two pictures of essentially the same spot. And what's happening here is in the first picture, it's just a regular picture. Like this is what you would see. The second one, the picture is through a polarizing filter. So it's blocking the glare, and you can actually see more of the detail underneath the water. So polarized sunglasses can be very helpful, at cutting glare. And so this happens to be just, how the light, bounces off the surface. And the way I like to describe it is, if you think about like the light coming down to the water, if it's shaking up and down versus shaking left and right, think about like a rock. You ever skipped a rock on the water? There's basically two ways you can throw the rock. You can kind of throw it like horizontal, or you can throw it like vertical. One of those skips a lot better. Does that make sense? And so when these waves hit the water, one of them bounces a lot easier than the other, which is why they tend to become polarized. So that's the last thing I'll mention about that. So we'll stop the notes here. That gives you some ideas about